Hey everyone, in this video we're going to talk about one of the 6 attributes of polynomials. Okay, so I'll be making 6 videos like these, breaking down all the different attributes of polynomials individually. Okay, so for this specific section we're going to be talking about the degree and the leading coefficient. When you're looking at a polynomial, these particular things or attributes of the polynomial will tell you a lot about how it looks, where it's pointing, and what type of behavior you can expect from a polynomial based on the degree and the leading coefficient. So let's begin. The degree. Degree is another word for exponent. Okay, so the degree of a polynomial is the highest exponent of that polynomial. Now, in general, a polynomial is written in this form. We have some coefficient in the front, x to some power, plus another coefficient, x to another power, plus c, x to another power, plus dot, 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 right? And it'll continue. Now, as we go higher than x squared, right, we have x cubed, x to the fourth, x to the fifth. We have all of these polynomials, and usually they're going to be writing the exponents in decreasing order. So if we have like x to the fourth power, the next one's going to be x to the third, x squared, x, and then the last number, right? Usually it's going to be written in that notation where it's the highest degree is going to be in the front, and then it goes into decreasing order. Okay, so as an example, when we dealt with parabolas, when we dealt with quadratics, we said this. Something like 2x squared plus 3x plus 5. Notice how here the degree of the polynomial is squared. This whole thing is a quadratic because this exponent, x to the second power, was the highest degree, telling you that this is going to be a U-shaped kind of function. Now, here in the front, we're dealing with the leading coefficient, which we'll talk about in a little bit, but this is the degree of the polynomial. Right? This tells me that this is going to look like a quadratic. Notice how the exponents go in decreasing order. We have x squared, x to the 1, and then no variable. This could easily be shuffled around as well. It doesn't have to be in that order for you to see that it's still a quadratic. So let's say that we shuffle it around and we have something like this. 3x plus 2x squared plus 5. Is this still a quadratic? Absolutely. The one in the front is not x squared, but notice that out of all of them, I just reshuffled these two right here. This is still an x squared. Therefore, the degree of the polynomial, or the highest exponent, will always tell you the shape of that polynomial. So when you're looking at a polynomial, no matter what it looks like, maybe it looks something like this. Maybe we're dealing with negative 5x to the third plus 4x to the fifth minus 7x squared plus 2x plus 3. If you're looking at a polynomial like this, the first thing that you want to do to look at the shape or the type of behavior you're going to be dealing with is first identify what is the degree of this polynomial. What is the highest exponent that I'm dealing with? And if you notice, the highest exponent is right here. Right? The highest exponent tells me that this function is an x to the fifth kind of function. And knowing that it's x to the fifth, that degree affects the rest of the picture, the rest of the graph in terms of its behavior, what it's going to look like, where is it pointing, all of that kind of stuff that we're going to be getting to here in a minute. But the first thing you want to identify is the degree. And the degree is the highest exponent of a given function. So the degree of this polynomial is 5. Okay? Everything else will also affect the polynomial, but we know that this is a degree 5, therefore I know what kind of a function to expect. Now, when you're looking at the degree, we want to identify whether it's an even degree or an odd degree. Is the exponent going to be even or odd? And that'll also affect the behavior of the polynomial. So I'm going to draw this right down the middle. Even exponents, I'm dealing with like x squares, x to the fourth, x to the sixth, x to the eighth. Anything that has an exponent of those types of powers, an even degree, will have a similar behavior. Anything with an odd exponent, like maybe it's just x, right? That's technically x to the 1 power, so just x, or x cubed, or x to the 5th, or x to the 7th, and so forth, right? The odd exponents will also behave differently. Now, the reason why I start here with x squared and x is because I like to think of things in the most basic fundamental forms. If I can break things down into the most basic, simpler forms that I can remember, then the rest will have similar behavior. Okay, so let's talk about what an x squared function looks like and an x looks like. Okay, and we'll go from there. An x squared looks like this. Let's see. Looks like a parabola. And then over here we have the x, which looks like a line, right? We spoke about these in Algebra 1 and also the beginning of Algebra 2. So your parabola has your 2 arrows, and your x has also 2 arrows. Let's look at x to the 4th, x to the 3rd, x to the 5th. Let's look at these other ones. Okay, this x to the 4th is going to look something like this, while x cubed will look something like this. On the left, we have x to the 6th, which can look something like this. While x to the 5th will look something like this. Okay, now if you haven't noticed by now, right, one thing that is making everything that has an even exponent in common is that the arrows, the end points, the end behavior is always pointing in the same direction. So if the parabola is pointing up or it's pointing down, the arrows are both pointing up or down, right? X to the 4th, the arrows are both pointing up, or I can easily flip it and make it point down, kind of like x to the 6th, right? The higher the degree, the more curves it'll naturally have, the more changes in direction it's going to possibly have. Now, the exponent can tell you how many possible x-intercepts we're going to have, but we're going to talk about that later. One thing we want to know for sure is that when it's an even exponent, whenever it's even, we want to make sure that we know that the arrows are pointing in the same direction. Okay, the arrows point in the same direction when it's even. When it's odd, what do we notice over here? The arrows are now pointing in opposite directions. Yes, as the exponent increases, we have more curves and more waves and more ups and downs, right? Maximums and minimums as we get to it. But regardless of however many curves or shapes it's going to have, odd exponent functions or odd degree functions, the arrows are pointing in opposite direction. So the biggest key thing to take from this is that even exponents arrows point in the same direction, and for odd exponents, they point in the opposite direction. So that'll already tell me the type of behavior that I can expect when I know that the highest degree or the highest exponent is an even number. Think of a parabola. Okay, the arrows are pointing up or they're both pointing down. Odd exponents, think of a line. The arrows are pointing, regardless of where they're pointing, right? They're pointing opposite to each other. So let's get more specific of how do we know when the parabola is pointing up or pointing down? And this is where the leading coefficient kicks in. The leading coefficient, right, as we spoke about earlier, is that we're looking at the highest degree of the exponent, this a x to the exponent plus bx to the next exponent plus cx, right? Let's just assume for a second that this is the highest exponent we're dealing with, and that it's actually in order from largest exponents to decreasing exponents. Let's say that this right here is the leading degree, or the highest degree of the function of the polynomial. Then this a value, this coefficient, becomes the leading coefficient of the entire function. That leading coefficient will tell you when it's pointing up or when it's pointing down, or where the arrows are going to be pointing based on the function we're dealing with. Okay? So, let's say that we're dealing with evens first. Let's talk about even first. Even degree. Let's say that we have a quadratic pointing up versus pointing down. We know the difference between pointing up and pointing down when this function in the front, when we have f of x equals ax squared plus bx plus c. When this a, this leading coefficient that we're dealing with, when it's positive, it's pointing up. When a is negative, it's pointing down. Okay, and that is true for any even exponent. If we're dealing with the to the fourth power, say that we're dealing with something like this versus something like this. Right? Say that we have f of x equals ax to the fourth power plus whatever's left. Right? Because it's to the fourth power, we're going to have more loops and more curves. But this a value, if a is positive, the parabola is pointing up. Or, sorry, in this case, the function to the fourth power is pointing up, and when a is negative, it is pointing down. So when it's even, the rule is simple. If it's positive, both arrows point up. If it's negative, both arrows point down. Now let's talk about what happens when we're dealing with an odd exponent. Okay, if we're dealing with an odd exponent, now the arrows are not pointing in the same direction. Now the arrows are pointing in opposite direction. So let's start with a very simple one that we spoke about, like in lines, right? If we're dealing with something like this versus something like this. Now when you're dealing with lines, your function is really just y equals mx plus b, right? Since we're dealing with y equals mx plus b, how do we know when the arrow is pointing up or pointing down? Well, the leading coefficient here is called m because it's for slope, but it's going to be the same thing as up here, right? The leading coefficient is the number in the front, the a. In this case, it's the letter m. We can call this ax plus b. It doesn't really matter. That will tell us when it's pointing up versus when it's pointing down. If the slope is positive, notice how the arrows are going to be going increasing upward. If the slope is negative, the arrows are going to go downward. So, similar thing here. The leading coefficient, we can call it m, we can call it a, we can call it whatever we want. All right? If a is positive, as x increases, the function is going to go upward. When a is negative, as a function increases, right? As the function goes to the right, the function is going to go downward. So the function increases or decreases depending on that value. Same thing with cubic functions. Let's say that we're dealing with x cubed. All right, let's say that we're dealing with this other function. Ax cubed, plus bx squared plus cx. Let me make some space here for you so you can see everything. Ax cubed plus bx squared plus cx plus d. Out of this entire polynomial, really, the only thing that matters is that we have an x cubed function, and this number will tell us if it's positive or negative. Now, notice how in this first scenario, there's a lot going on here. But as the function goes to the right, as the x value on the x-axis increases, what happens to the function? It goes up. This means that the a value here for this cubic function, this cubic polynomial, a is positive. Because as it moves to the right, the function increases. On the other hand, notice how here the function eventually will go downward. If it eventually goes down and it decreases, that means that the a value must be negative. Okay, so we could deal with x to the 5th, x to the 7th, anything. This number in the front, the leading coefficient, what will it do eventually? If it's positive, it will eventually go up. And this could be really anything. We could be talking about, let's say something, let's put something here on the side, something a little bit more ridiculous. Let's say it looks like this. It's got a lot of loops, a lot of stuff going on. What is really happening with this? As the function goes to the right, where is it going to go? It's going to go up. If it's going to go up, that means that a has to be positive. Okay? Just like that. So now let's put these two things together. Let's talk about leading coefficient and the degree so we can actually put it all to use. Now that we know that the degree is even or odd and the behavior, and we can look at the leading coefficient in front of that degree, and it'll also tell us where the arrows are pointing, now we can get a really good image of what a function does. So let's talk about some examples here. Let's say that we have something like this. Okay, notice how here, if I'm looking at this polynomial, both arrows are pointing in the same direction. So what can I say when both arrows are pointing in the same direction? The exponent is even. We're dealing with an even degree, even exponent. Whatever it is, it's an even number because the arrows are pointing in the same direction. Now, because it's an even number, right? Let's say that we have the general form will be like this. F of x equals a x to the even. This is my exponent. The exponent is even. What do I know about the a value? Well, a here, look at the arrows. Where are they pointing? They're pointing up, which means a must be positive. Right? The leading coefficient is positive, and the exponent, the degree, is even. Let's look at another one. Let's say we have something like this. What is the degree of this polynomial? Well, notice how the arrows are not pointing in the same direction as we did here. Now the arrows are pointing in opposite directions, so the degree must be some odd number. Whatever polynomial we're dealing with has to be an odd degree. That's the first thing we want to make note of. It's odd. X to the 5th, x to the 7th, x to the 9th, x to something that's an odd exponent. Now, if we're dealing with an odd exponent, then it's look like this. F of x equals a x to some odd number, right? You fill in the blank. The odd number in the top could be 3rd power, 5th power, 7th power, 9th, 11th, anything that's odd. What do we know about this leading coefficient? Is a positive or is a negative? Well, let's study the function. What happens to the polynomial as it goes to the right? It will eventually decrease or go down to the negatives. Therefore, a must be a negative polynomial. So here we have an example on the left of an even polynomial and an odd polynomial. We can describe the behaviors based on the exponent, whether it's even or odd, and the leading coefficient, the a. It'll tell you where the arrows will be pointing. What if I give you something like this? Let's kind of wrap this all up by doing this. I can also even give you a function. Let's do this. 2x squared plus minus half x to the fourth plus x. Here we have an example of a polynomial. The first thing we want to identify is the degree. What is the degree here? The degree is the highest exponent. Here the degree is 4. And it's even. So because it's an even degree, we know that the arrows point in the same direction. Okay? So it'll probably look like the picture here somewhere on the left because it's even. The arrows point in the same direction. Now, what about the leading coefficient? The leading coefficient, now that I know that it's x to the fourth power, right, the leading coefficient is this number in front, the -1/2. That'll also tell me something about this polynomial. This -1/2 is the leading coefficient of x to the fourth. So because it's negative, what will it tell me? Because it's negative, it means that the arrows are pointing down. So if I'm going to do a sketch here, this is what I can expect. I have the degree is even, right? So the arrows are pointing in the same direction, and the leading coefficient is negative, which means that those two arrows are both pointing down. And the polynomial will look something like this. Because a is negative, and because the exponent is even. Both arrows point in the same direction. And voila. That's pretty much it, guys. If you know the exponent, the degree of the exponent, whether it's even or odd, and if you know the leading coefficient, whether it's positive or negative, it could be a fraction, it could be a whole number, it could be anything. Then you'll know where the function is pointing. And you have a very clear picture of an overall view of any polynomial. It could be x to the 7th, it could be x squared, it could be x to the 31st, it could be anything. You know what it looks like, you know what the arrows are pointing, and in what direction they're doing that. All right, I hope this helps. Let me know if you all need anything. Don't forget to like, and if you haven't subscribed already, what are you waiting for? All right, guys, as always, I'll calc you later.